interesting possibility in terms of power consumption, in terms of speed, bandwidth, and application. Come faccio andare avanti? Ok. Ok, fine. So this term appear in everywhere in the last year. Optical computing, analog computing, photonic, analog chip, not only in scientific journal, but also in newspaper and magazine that usually treat other kind of matter. And a number of spin-off startup and companies received huge investment for this field. Tens of billion, it means budget that are orders, plural, of magnitude larger than our Restart project. Analog photonic computing, what does it mean? Oh, grazie mille. So analog means photonic is a wave. So is analog by nature, and we have to think about an analog processing. Photonic means that we can process the information, the signal in the optical domain. And computing means make a calculation. So make a calculation in the optical domain, not digital, but analog. Most of the interconnection is in fiber and in space optics is in optics. So the information is in optics, and the possibility to process and work directly on the signal in optics is a great advantage, clearly. You can preserve the phase, you can preserve the polarization, you can work with multi-channel system. And so the question is, can we in some way try to do the processing directly in optics? So digital or analog, electron or photons. These are the two fields, basically. Photons have this characteristic, well, they have many characteristics, but we can say weak interaction with the material, weak interaction between them, very poor nonlinearity, and good point, we don't need metal for optics, so no skin effect. We can transmit at 1 bit per second or 1 terabit per second, and the attenuation is exactly the same. Reduced latency and large bandwidth clearly are the characteristic of optics. So it is suited for linear analog operation. No non-linearities. In comparison to electrons that have a strong interaction between them, strong non-linearities, and have the possibility to be stored somewhere. And every time you have to move electrons, you have to charge or discharge the capacitance, so the cable. And this is really a problem for high-speed transmission. So computing is misleading. Computing is not in the sense of the electronic computing. It's something else. It's processing and is in linear. But linear means algebra. And with algebra, you can do a lot of things. Let's go back to electrical domain or to electronics. Usually we use a formula to explain the behavior of something. But try to think in the reverse way. Use this circuit to make this calculation. So you have to do the multiplication 3 by 2, take a resistance of 3 ohm and send inside a current of 2 ampere and read the current, the voltage across. So this is analog processing, and this multiplication that is very easy in electronics and also in optics. And with a slightly more complex circuit, you can do the sum and also the multiplication, but basically you can sum the two current and read the current through. So this is two very simple case, and is at the base of the first analog electrical computer. This one, it's very nice. The screen is more similar to an oscilloscope than to a screen, and you can do a lot of things with this object. And this is the beginning of the electronic era. Also in photonics, you can do something similar. For example, the blue line are photonic waveguide, and this is a resonator. So you connected by this way, the output in time is related to the input through a differential equation. So you can solve the differential equation by reading the output of this. This is an example for differential integral operator, but there is something else. For example, algebra. Here we have a circuit with this interferometer. It's called Mach-Zehnder interferometer. And we have a number of input, a number of output. This is linear, so this can be described with a matrix. So this circuit solves a system of linear equation. A matrix is a lot, and the two examples here are not just reconfigurable circuit or tuning or calibration. It's really programmable, because you can program the circuit that is a general purpose to do something. And you know that with a matrix, you can do a lot of things. You know probably better than me that the output is the sum of the input weighted by these coefficients are inside the circuit inside the Mach-Zehnder interferometer, and you can do convolution, equalization, filtering, any kind of transform, and even the convolutional layer of the neural network. So with a matrix, and this is matrix vector multiplication, you can do really a lot of things. And also matrix by matrix multiplication. All the algebra can be achieved with this kind of circuit. Let me go inside this circuit and give me just a few seconds to explain one of these gate, one of these interferometer or Mach-Zehnder, and the blue line are the waveguide. There are two directional coupler. This interferometer has an imbalance that is 0. It means that the bandwidth is huge, theoretically infinite, and you have the input. The input are wave, so are complex number, amplitude and phase. You multiply the input by this matrix and you get the output. If you add a little control, it should be electronic control, that change the two phase inside the circuit, you can add the two input and send the two input to the output. You cannot add two wave. You cannot add the two field. You can add the power. And so the power here is 0, and the power here is the sum of the power of the input one. So this is the most simple adder that is able to sum the two input wave without any knowledge about the input. It is important. You don't need to know the vector x to perform this one. Just knowing nulling the output here with a dedicated analog electronic circuit. The transfer function of this is very, very smooth. It's very simple, just two sinusoid, so there are no local minima, and the convergence always happen. Okay, application. Suppose you wanted to transmit a free space beam to the top of the Vesuvio. We are here. At every talk, I change the photograph of the place, clearly, but it's good. You send... scusate, va bene. In effect, the alignment of the beam is always a problem, in effect. As in the field. And, okay, you send a Gaussian beam, very focused, you wanted to arrive at the receiver, but what you receive instead is not the nice, smooth Gaussian beam that you send. It's something that is strongly perturbed. In our language, is a multimode field, because you excited multimode. And this is due to the air that is in between, that can have temperature gradient, can have wind, rain, or even ash sometime, and disturb this. So this is our acquisition of the beam done on the roof of our department in Politecnico of Milano. This was in the... I don't know how to go back, but not a problem. Okay, this is during a very hot day in the summer, and this is during the night. In any case, it's not a Gaussian beam. So the problem is how to convince this multimode beam to enter in an optical fiber or in a very small photodetector. Because if you wanted to transmit at a very high bit rate, gigabit per second, 100 gigabit per second, you need a very small photodetector. So you have to be single mode and not multimode. But if you understood the working, how it works, the single adder, once you add this to sample of the incoming beam, you can add the third one and the fourth one, and so bring all the power to the output here. And this is a single mode. At this point here, you can place an optical fiber, you can place a photodetector at very high speed, and the signal is in the optical domain. So it preserves the polarization, preserves the phase, if you have a multiple channel. So we built the circuit, we put some electronic around with my colleague Marco Sampietro from Politecnico of Milano. We try to package everything, and we realize the photonic computing. This is photonic computing. Once again, it's not the computing in the sense of the electronic, but is the multiplication of the input vector, complex input vector, by a matrix. So is algebra. For those who do not believe, this is an experiment done in the lab with a signal. There is no turbulence, no perturbation of the free space path. And this, we switched on the turbulence, and then we switched on the control. And this is the signal that we received, the probability density function of the signal. And as we switch on the control, you see we have more power. And this is good, but amplifier exists. But what is more important, you see, it's very confined. The spread is really very, very smaller than in the case of turbulence and no control. So we tested at 10 gigabit per second and 25 and 50 gigabit per second. Then we played with PAM4, and we played with some let's say, analog signal, let me call it 1024 QIM analog. We played with WDM and also with signal in chaos communication for security, and we achieve a very good result. What we are doing from a mathematical point of view, we are doing a singular value decomposition of the matrix. So a singular value decomposition means that every matrix, rectangular, symmetric, even singular matrix, can be decomposed in the multiplication of three matrices. D is diagonal and is implemented with just this simple circuit, and two unitary matrices that can be implemented with this circuit here. So if you need a matrix, you can implement physically on a photonic chip by cascading these three. This is the synthesis of the matrix. The analysis is even more interesting because you can really calculate the matrix of the system using these two matrices. So this is a known matrix. For example, the matrix that describe the link, the channel where you transmit. The matrix can be decomposed in these three matrices, unitary, diagonal, unitary. And if at the transmitter and the receiver, you add two unitary matrices like this, and you tune this matrix in order to maximize the power here, you can cancel, you can make this one equal to V, and U DAG equal to U. So this one by this one is the unitary matrix, V DAG by V is the unitary matrix, and you get D. So you can measure the matrix of the channel. For those that do the channel estimation, is something that is interesting. And this is done during the transmission of the signal. So it's really a joint communication and sensing system. So we played by putting some matrix in between. So the system, if you don't put nothing, it's just a free space, and the beam that which you converge are the classical Gaussian beam. You see more beam because are the spurious mode. The antenna are separated by more than half a wavelength, so you have the other order. So this is the classical Gaussian beam and the second Gaussian beam. But if you put something in between, you can find the eigenvector of the system that corresponded to the best channel. These two modes, difficult to believe, are orthogonal, and so they do not exchange power and are the best channel of the system. And we played also with the logo of Politecnico. So these are the eigenvector of the logo of the Politecnico of Milano, calculated hardware with a photonic processor. Probably for the first time, I guess that in the past someone tried to calculate the eigenvector with MATLAB or something like this. And this two mode, the comment of the two channel of the two mode are orthogonal, are fully orthogonal, but not because we are good in using this system and calibrate the system, because it's orthogonal by nature. It's the matrix itself that is orthogonal. And this is very important. Have a look at this shape of the mode. Are not the classical mode, are not Gaussian mode, are not the Bessel beam, are not angular orbital momentum beam. It's something else. But these are the best channel and are not are orthogonal. So this is just an example, but we played clearly with other group around the world. We distribute our chip to other group, and with Stanford University, we played with a neuromorphic, clearly a neural network, you can do only the linear part, not the non-linear part, because the non-linearity, let me say, is difficult to do with respect to some colleague. And the paper was published on Science. Or the hashing for the cryptocurrency. You have in a cryptocurrency miners, you have to continue to do continuously the same operation. So this chip is perfect because continue to do it at the speed of light. And you don't have to do nothing, just go around and wait for the correct answer. And another example is, this is the video of the in situ backpropagation of the neural network. I stop. In situ means that you can do it on chip while the chip is working. That is why it has been published on Science. Or the matrix inversion. The matrix inversion, you wanted to invert the matrix A in this system, can be written in a recurrent way in this way. So put this photonic chip inside the loop and automatically it converges to the inverse of the matrix. It's algebra, it's linear, so we can do it, no problem at all. And last slide, a lot of space for this photonic computing in not only in telecom, in datacom, in data center, to make switches, to make the transceiver, but also in many other applications. Routing, the LiDAR in automotive, drone, in optical hashing, quantum key distribution, the circuit that we use. I'm a classical guy, I'm not a quantum, but people from quantum like our circuit and use them. And in bio and medical. But if you look at the market, the 99% of the product are transceiver. And almost nothing on this side. That is a good news at the end, because there is a lot of space for improving and a lot of space for this kind of approach. So this concludes my talk, and so we start at the beginning with analog. At the beginning of the story was analog 70, 80, 90 years ago, and then we moved to the digital era. But we are going back, and photonic can help. I don't say that photonic substitute the digital electronic and digital computation. Electronic and photonic collaborate, are synergic, and must work together. But they can solve a lot of problems. And this is a nice, we place our chip on a PCB. These are the two CMOS ASIC designed and built by my colleague Marco Sampietro, directly connected with the chip and able to control directly. The next step will be put the electronic inside this one. But this is another story. Thank you very much.
Andrea, for your presentation, quite an interesting point of view, and the contribution is open for discussion if there are questions for Andrea. If not, I have one. Are you looking something?
No, it's too late.
No, it's not too late. You said analog optics cannot replace digital electronics. But you somehow intend that it may replace analog front-end electronics?
This is a good point, yes, especially if we think to our story. In a system, you can do everything in optics, or you can do everything in electronic. The important point is to find where stop the optics, convert in electrical domain, and start with the electrical domain. And this point depends on the application. But
So it's
yeah.
application driven.
Yes, absolutely.
Oh.
Yes.
Yes. Aspetta. Non ti sente. Vediamo, passa un po'.
Well, the chip itself, the photonic chip, does not consume nothing. It's zero, really. But you have to generate the light, inject the light, and use the photodetector, and so on. And this consumes, obviously, light. I think that the big advantage comes with the scaling. Once the function becomes complex, the circuit becomes complex, there is no doubt that the photonic approach has an advantage in terms of power consumption. Yes.
Thank you.
Any other question for Andrea?
Yeah, I'm not sure this is a proper question here, but is it universal, this circuitry?
Universal means
in terms of computing.
General purpose.
Yeah.
Well, the mesh of Mach-Zehnder is a matrix. So every application that needs a matrix, basically everything, can take advantage of this circuit, for sure. The way we calibrate the matrix instead depends really on the application. The free space optics case, it's automatic because you need to find the minimum of the power or maximum of the power, so it's automatic. In the case of the inversion of the matrix, you have to calibrate the circuit to make the matrix that you want, and this is more complex.
Okay, thank you, Andrea.
Thank you very much.
Grazie, mi preparate quel video. Allora, resilienza, no? Ripresa, restart, ci siamo. Resilienza, resisto a uno shock emotivamente, psicologicamente e anche con il mio fisico mi riprendo. Siamo resilienti? Beh, mi sembra che il restart lo sia. Organizza un convegno, ci convinciamo di fare cose nuove, cioè presentazioni innovative di qui di lì. Le rifaremmo in maniera completamente diversa la prossima volta, ma le abbiamo fatte. Perché resiliente? Ma voi siete venuti, c'erano gli incendi e siete arrivati. Siete venuti, c'è stato il terremoto e abbiamo continuato. Accidenti, più PNRR di questo non c'è. Quindi effettivamente restart, oltre che è stata ripresa, è stato anche ed è resiliente. La resilienza si assesta nel tempo. Questa struttura che vedete, il contenitore, è disponibile per chiunque voglia adoperarlo almeno fino al 31/12, poi con nostre risorse anche dopo, perché è un contenitore che permette di esprimere le cose come prima non si esprimevano. Questo non è un convegno ed infatti abbiamo lavorato, stiamo lavorando, completeremo questo tipo di attività. Adesso la resilienza ce l'hanno insegnata, noi la sappiamo da un sacco di tempo e la conosciamo perché chi è in Federico II ce l'ha come carattere istitutivo la resilienza. Prima mi hanno detto ma nell'introduzione non si è parlato molto di Federico II, eccetera. Allora io vi faccio sentire cosa ha scritto Federico II 800 anni fa in questo video, che è un video della Federico II. Quindi tutto sommato ci ha dato il programma. Noi professori dopo 801 anni non l'abbiamo completato. Sentite esattamente le parole e capite che razza di programma per noi professori è. Ecco perché realizzare una cosa in PNRR significa una cosa che serve agli altri. Ma sentite le parole di Federico II. Le immagini sono le immagini degli oggetti creati da Federico II. Tutti quegli ambienti sono la nostra università. Non vedete il Vesuvio, non vedete queste cose qui tipiche di Napoli. Vedete proprio i luoghi di Federico II. E alla fine c'è il messaggio che noi diamo ai nostri studenti, ai nostri giovani. In fin dei conti questa è Next Generation. Il messaggio è che quel tipo di messaggio è, vabbè, lo sentirete i ragazzi cosa dicono. Quella cosa che dicono quei ragazzi, perché sono in questo momento in Federico II, lo può dire chiunque è in Federico II. È Federico II, chiunque in questo momento, anche ora, tutti noi, fa parte di questo sistema. E allora non è un caso, ma il presentatore adesso è Federico II, io non sono salito apposta sul palco, prego.
Desideriamo che in ogni parte del nostro regno molti diventino savi e accorti, attingendo alla fonte delle scienze e a un vivaio di saperi. Disponiamo perciò che nella amenissima città di Napoli vengano insegnate le arti e coltivati gli studi connessi con ogni disciplina, così che i digiuni e gli affamati di sapere trovino nel nostro regno di che soddisfare i propri desideri e non siano costretti, per ricercare la conoscenza, a peregrinare e a mendicare in terra straniera. Intendiamo così provvedere al bene di questo nostro Stato, mentre con la grazia del nostro speciale affetto curiamo i vantaggi dei sudditi, i quali, come si conviene, resi edotti, possano essere animati da una bellissima speranza ed attendere con spirito pronto molti beni. Dunque siano felici e pronti agli insegnamenti gli scolari che desiderano a essi essere incitati. A loro procuriamo ogni cosa utile, offriamo buone condizioni, riserviamo illustri maestri, promettiamo beni e a quelli che ci sembreranno degni offriremo premi. Vi promettiamo di rispettare le condizioni proposte, di onorare le vostre persone e di ordinare universalmente che da tutti siate onorati.
Io sono Federico.
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 Grazie. Dunque, continuiamo questa sessione con un intervento di Leonardo Viti del CNR dal titolo Terahertz Optoelectronics for Free Space Optical Communications. Penso sia meglio questo.
Grazie. It's nice to start after the video, very motivational. I like it. And so thank you for having me here. And what's terahertz optoelectronics? Well, it is still not clear the role that terahertz will have in future communication systems. And it is still a matter of debate. And of course, I'm not here to solve this debate. What we have kind of understood is that we will use terahertz radiation, even though we don't know at which extent we will use it. In this talk, I will give you an overview of what are the main challenges that terahertz communication systems have to face, and what are the main use cases. And this will be done with a specific attention to what has been done in the Restart project, in particular in the DREAMS and TNEX projects, and in particular on the device side. If you pass from the exhibition, from our space in the DREAMS project, you have seen some of these devices that we are working on. So let's start with very simple question. What is terahertz? It is a quite difficult frequency range between 100 gigahertz and 10 terahertz. And it is difficult because it's between electronics and photonics. And if you sit from the electronics point of view, you will see that terahertz frequencies are difficult to reach with standard electronic devices. And if you sit from the point of view of photonics, the energy of terahertz photons is very low. For this reason, there are no semiconductor devices which can, standard semiconductor at least, which can absorb or generate terahertz photons very efficiently. Despite this, this kind of a frequency range has a lot of applications, and some of them are now moved away from the academic world and come into real-life applications like security control, industrial control, and astronomy. Besides these more traditional applications, some new ones are emerging, and one of these is for sure high-speed communication. Now the idea between terahertz radiation and high-speed communication is that the demand for higher bandwidth needs the frequency of the carrier waves to shift from tens of gigahertz to hundreds of gigahertz to the terahertz range. And if we look now at what are the challenges that are brought about with this increase of frequency, we can see that it will not be easy to have terahertz channels. The first reason is that terahertz is strongly attenuated in air. In this graph here, you see that the attenuation is very strong in the terahertz range, and this brings immediately two consequences. We expect terahertz free space optical channel to be very short range, and second, we expect them to be directional. If you don't want to lose power, as we have seen this morning in the talk by Ciaramella, if you don't want to lose power, you have to work with narrow beams. And now working with narrow beams brings a second challenge, which is blocking. Basically, imagine having terahertz links in a room crowded with people, and these people moving around will be blocking the beam because it will be small, like 1 inch in diameter. Now, some people in the terahertz community have started thinking of this as an advantage. You see here these green lines is a communication between Alice and Bob. And there is an eavesdropper, so someone who wants to intercept the communication between Alice and Bob. And since a blockage can be readily seen by Bob, it will be difficult for Eve to get a message without being discovered. I'm not so sure about this concept in the terahertz community that it's really better to, with respect to eavesdropping, but I will just leave this here, okay? Another challenge is the availability of power. Power intending emitted power. You see here a chart where we have the emitted power per device as a function of frequency, and you can see that regardless the material that you use, the power available will go down. A possible way to work around this situation is to use an array of emitters. For example, an array of terahertz radiators. And interestingly enough, what you can do is that you can tune the phase of these radiators on its plane, and basically you can engineer the wavefront, so you can steer the beam directly at the source. And this, for example, could cover some of the blocking issues. And now let's see what are the use cases. So given these challenges, what do we expect we could be doing with terahertz radiation? So the first use case is an indoor scenario where you have a very short range link, like tens of meters, not more, and where you want to transfer data to more than one user and very fast. This, for example, is called information shower or kiosk downloading. Imagine a very small region. You can think of it like an airport, for example, where people have to enter a space where they can download every information about the airport in just 1 second, let's say. This would be an advantage, for example. Another important application that comes to the mind is backhauling. So you can replace one of the backhaul links with a very fast terahertz channel. This, for example, has been tried by Ericsson. They did a 1 kilometer terahertz channel with 100 gigabit per second speed. And another application, of course, is to get rid of atmosphere. So to go into the satellite communication. But as we have seen today, there are a lot of other frequency ranges which are probably more, let's say, accessible than terahertz domain. So, given this context, what have we done during this period, and what are we looking for? So, terahertz optoelectronics is a broad term that covers sources, photodetectors, and modulators. Terahertz optoelectronics needs devices that can have enough power, enough sensitivity, and enough versatility to carry information around. So we are looking for sources that are quite powerful, and for this reason we looked for quantum cascade lasers. We look for detectors that are sensitive and fast, because they have to sustain a certain bandwidth, and we worked with graphene photodetectors, and we looked for modulators that are able to change the direction of light. And again, we worked with graphene modulators. Now let's see these different architectures one by one. So first we start with quantum cascade lasers. These are semiconductor devices based on semiconductor heterostructures. They are quite easy to be used in the sense that you just apply a voltage difference and you get light output. They are actually difficult to be used because in the terahertz range, you need to cool them down at least a bit. And you can get very nice spectra, very nice powers out of these lasers. But what is important, let's say this, for example, this example here goes from 2 to 4 terahertz. What is important is that you can design your QCL, quantum cascade laser, to have a specific spectral content. And this is what we have done. And we have, for example, modified the waveguide of these lasers to have a specific spectral content. And this can be useful in communication environments because, for example, you might want to separate in the space the colors that are emitted by a quantum cascade laser. And with this multiple channel, each of which has a different color, you can address different photodetectors. In this way, for example, you can increase the robustness of your communication channel, and you can use multiplexing. So you can send a part of communication to one detector or to the other. Importantly, what you can do is you can also couple on the same chip different quantum cascade laser and combine their output together to get a wavelength multiplexing on chip. From the detector point of view, we have worked with the graphene. And why we choose graphene instead of other standard materials? Well, the interesting graphene is that because it has response times to optical stimuli, which are faster than standard semiconductors like CMOS. And it is also compatible with the CMOS technology, so you can mount your graphene detectors on top of a CMOS readout circuitry, and you can do it in a scalable way. You can really fabricate a number of detectors. So we have tried, and we are just at the beginning of this challenge. Let's say this is a small array, 5 by 5, that you can see at the exhibition. And what is important, why we are looking for arrays? Basically, if you have an array, you have multiple detectors that can increase the robustness of your channel. Let's say your beam is vibrating for some reason, and the central detector will not always be in the maximum, let's say, signal. So you will need adjacent detectors to receive a part of the signal, and they can tell you which kind of signal you are transferring. And importantly, another thing that you can do, you can do spatial multiplexing. So you can send one channel to a portion of the array and another channel to another portion of the array and process it on the same device. From the modulator point of view, again, we use graphene. Graphene is a sort of a special material. You can basically change its optical response by applying an external gate. So you can change the number of carriers, and you can make it more transparent, more opaque, more reflective. And if you work in reflection, this is just a 2 by 2 array, very simple. You can see that you can change the reflectivity of each pixel by simply applying an electrostatic gate bias. And you can imagine doing it on a larger scale. So you can imagine having more pixels and applying, let's say, different columns, different colors to different columns. So having like a bright column and a dark column, and so on and so forth. And in this case, you are basically creating a diffraction grating. And if you have a diffraction grating, you can steer a beam, especially if you can decide which columns are on and off. So it's a reconfigurable surface with which you can pilot a beam, for example, generated by quantum cascade laser. Now, with this number of devices that you can think of, we have tried to build a free space optical communication link in the terahertz range. And we have, of course, we started from the simplest case possible, which is you have a quantum cascade laser. In this case, you can see it there in the cryostat. And we tune the intensity of the quantum cascade laser, and we encode in this modulation a message. We encode a packet of information, and we send this terahertz beam, this free space optical communication channel, onto a graphene photodetector. And basically, we were able to, let's say, find terahertz communication, error-free communication, and we tested this as a function of distance. You can see here that the setup is mounted on these cards. The cards are mounted outside the lab, so the light gets in the lab, then outside again, and we move away from the lab. So measuring how far we can go with this terahertz link, we didn't go very far. We just go a few tens of meters, I would say totally 10 meters. And this is, of course, to be improved, and we are working on it. And interestingly enough, we are not the only one working on it. There is a group in United Kingdom that now made some sort of the same technology, just 6 months our publication, in which they show that this kind of link can go up to 4 gigabit per second, which is not bad for the terahertz range. And I will just conclude my talk with a question, which is terahertz ready? And using the citation of Roberto Verdore this morning, that was, when it comes to prediction, the expert is always wrong. So maybe it's not a good idea to make predictions, but let's try to have this exercise together. So on this graph here, you see on the horizontal scale, there is a distance. So these are close application, like board to board, chip to chip, then data center, and the far you go, you see distance increases. There are satellite sensing and satellite communication up here. On the vertical scale, you see mobility. So on the ground floor, there are applications which are stationary. They are static, they're not moving. As you move up, you find people moving, you find vehicle moving, you find the satellites, and so on and so forth. So is terahertz ready for this kind of environment? And I think the honest answer is depends what you call terahertz. So if by terahertz we intend the frequency range from 1 terahertz to 10 terahertz, let's say the red zone, I would say it's very difficult to imagine it working on long distances, especially for terrestrial application. I would not expect it to go beyond tens of meters. If you want to go farther, you need to go down in frequency, so to use the millimeter waves, let's say from 30 to 300 gigahertz, more or less. So let's say with this question to myself, actually, I would like to conclude the talk, acknowledging the colleagues and the people that work with us in the DREAMS project, and of course, thank you for your attention.
Thank you, Leonardo. The paper is open for questions. Are there any? Well, I have just one remark. In my high-frequency electronic course, because I teach high-frequency electronic course, I say that basically while moving from millimeter waves up to terahertz, really things becomes easier. Because you pass from the 3D Maxwell's equations to something much easier that is easier to manage. But from the practical point of view, this is not the case, because you have many problems while dealing with optoelectronics. So, for instance, dealing with inter-satellite links, for instance, there is a big debate on doing inter-satellite links, optical or RF. And it seems that Starlink is going optical, perhaps, but we don't know really. But we have problems in handover. We have problems with the acquisition of signal. So can you comment on that?
Yeah, so the terahertz frequency range actually is inheriting some of the challenges from both sides. So if you think about optics, right, you will still have the pointing issues, even with the terahertz, because you need to point somewhere, right? Yeah. This pointing can be mildly mitigated in atmosphere, where, for example, you have less scattering issues with terahertz because your beams are a bit larger. It is kind of more robust to Rayleigh scattering. But outside the atmosphere, if you think of satellite communications, terahertz SAT-to-SAT communications will suffer the same problems that we have seen this morning in the talk by Cialamella, where you still have these pointing issues. They will be ubiquitous, and they will stay there also for the terahertz. This will not be solved by changing frequency, let's say. So again, the debate is open, and we are able to, let's say, produce some devices, but the use cases is, let's say, a question to the whole community, actually. It's not only a question to us, but it's a question from us to you as well.
As the researchers, I mean, we are doing that. So, other questions?
Hi. Thank you for the presentation. Very nice. So do you have any idea what is, let's say, or an estimation of the ultimate frequency modulation that you can achieve with your terahertz devices, more or less, or and exactly what?
With the lasers?
No,
Yes.
no. With the terahertz modulators. What
With
I
the
mean-
modulators?
Yes,
So-
modulation frequency, and what should prevent it to be larger? Because, I mean...
Yeah. So there are two answers. The first answer is, let's say the direct answer is that there are some examples of graphene modulator reaching tens of gigahertz. This is the first answer. There is an example of terahertz photodetectors being able to follow signals up to 400 gigahertz. Okay. However, if you think about modulators, there is another figure of merit that is often hidden under the carpet, which is the contrast. So you need to have a contrast between when your modulator is on and when your modulator is off. And this contrast figure of merit typically plays against the bandwidth. Because if you want to increase the bandwidth, what you have to do is typically to go to small devices, right? So you just have a resonator with a graphene piece at the center, and you change the behavior of the whole resonator by changing the behavior of the graphene piece at the center. But if you can maintain contrast and speed, then that would be a really big deal, and people are working on that, actually. But let's say the speed is not the only figure of merit in this case.
More or less along this line of the last question, considering the difficulties in increasing the rate and controlling, these kind of characteristics of the devices, do you think that other fields of application will come first, and then maybe when the technology will become more mature, we will see some more application in the communication domain?
This is already happening, actually. So let's say that we started from terahertz imaging with these photodetectors. And we were able, let's say, to kind of distort the design, passing from what is optimal for imaging and distorting it, adapting it to the communication environment. Domain. So this is, in the terahertz range, is already happening because the communication application is new. So there are a lot of things that we
can inherit it from the other applications.
We can inherit from other fields, other domains, and then we are trying to apply these to communication.
Thank you.
It seems there are no more questions. Thank you again. It is time now for the third presentation that is entitled Artificial Intelligence Meets Self-Free Massive MIMO, and that will be given by Giovanni Di Gennaro from Università of Vanvitelli.
Thanks. Point? Oh, thanks.
Okay, let me start with a question. Can you imagine a world where your connection doesn't drop just because you turn on a corner? Well, I know it may sound far off, but that's exactly what I want to talk about today. I'm Giovanni Di Gennaro, a researcher at University of Campania, and I work at the intersection between next generation wireless communication and AI, or rather AI as we know it today, machine learning and neural networks. And in just a few minutes, I'll show you how a concept called self-free combined with this kind of artificial intelligence can help us make that world a reality. Okay, but first, I want to take a moment to apologize to all of you, and especially to the organizer. I try. I really tried. But the more I study what a TED Talk is supposed to be, the more I realize I just can't do it. There are more reasons, and 3 personal reasons are probably the most one. I am a simple person, so I just can sell you something that does work. Or claim we are landing on Jupiter next year, if you know what I mean. Second, my life is just that exciting, so I don't have a movie personal story to trigger you the classical "oh" moment. I wish I did, but no Thursday, I'm afraid. And finally, probably the most tragic of all, my eyesight is perfect. No glasses. So my wife say, why not just wear empty frame? But well, this brings us back to the first constraint. So well, sorry about that, but this definitely will be a TED Talk. Okay. Now that we have cleared that up, let's start to the real topic of today's talk. Modern wireless communication. There are 3, maybe 4 stages we all experienced more time than we like. First stage, signal drop. Second stage, data slower to a crawl. And the third stage, total frustration. So yeah, I say 3 or 4 stages because there are a lot of people that react to this frustration in a rather creative way. They buy a new phone. So a big question arises, do we really need a new phone? Well, spoiler alert, probably not, but let's take a moment to understand why. Modern cellular network, as the name suggests, are built around cells. Each cell is managed by a single base station that handles all the communication within that area, all by itself. So here's a catch. No matter how much money service providers spend, and they're spending a lot to update and power this base station, because they are still up against an unbeatable opponent, physics. Signal strength doesn't drop slowly. They are typical in this form. So if you are close, everything is great. But if you're far, welcome to the frustration zone. Okay. And yes, this is the biggest issue of today's cellular network. And it's not just about distance. Is more of it actually come precisely for interference between cells. Okay, so but then we have also an over. On a single city street, your phone may switch from one cell to another multiple times, and every time it does, your connection takes a hit, losing a bit of itself. On top of that, we have a limited simultaneous connection, energy inefficiency, because, well, turn off a base station is rarely an option, and obviously poor fault tolerance. And just to be clear, 5G doesn't fix this problem, okay? So how we can fix them with a new approach? Well, to understand that, we have to make a little step back. In the beginning, one single antenna transmitted signals in all direction, wasting power and create a necessary noise, which turned into real interference when traffic grew. So then come MIMO. And we learned that adding more antennas means more data and better resistance to interference and noise. Massive MIMO pushed this idea even further. Many more antennas. With many more antennas, we can focus the signal like a laser beam directly toward each user. Less waste, less interference, better performance. So the lesson is, when it comes to antennas, more is better, okay? But here's another catch. It's not just about how many antennas you have. It's about the degree of freedom that you get. So, besides we have just shrunk, stacked, and optimized the antenna, we can just keep stacking into the same box forever. Okay, so what's next? Well, instead of adding more antennas in one location, we can distribute them across the area, adding a new spatial degree of freedom. This is the idea behind cell-free. And in cell-free network, multiple distributed access points are work together to serve all users. This is precisely this cooperation that break the traditional idea of cell, of rigid cell, okay? And of course, this approach has already shown, even in simulation, extraordinary results. High performance respect to 5G communication, and obviously more uniform coverage, improved load balancing, improved energy efficiency, because we can selectively turn off this small access point, okay? But, well, cell-free is not, cell-free network are something we can just deploy overnight, okay? There are still major challenges researchers need to solve before this technology may become a mainstream. Three are the bigger ones. Scalability, how to deploy the system and make them scale with the number of, with the growth on network. Synchronization, because each IP should communicate perfectly so that signal add constructively, okay? And association, deciding which IP should serve which user. And this is precisely where A could come in, okay? The very point of A is its goal. Its goal is not just finding one solution, okay, but learning how to generalize. So make the system work even in scenario it has never seen before. Obviously, machine learning and artificial intelligence has many phases, and we can separate them in deep learning, reinforcement learning, and further learning. But this is not very important. The important is what we can do with that, okay? Yes, each of it can help us to do something, okay? But As I said at the beginning, I can just sell you a dream that I don't have in my hand. So let's show you a real example, a working example of a scalable and efficient user access point solution system. Our work starts from a first goal. We need a network that could manage multiple users and different numbers of users and could scale with the number of users. Because surprisingly, most of the existing, still few, AI-based solution in literature start from the wrong assumption. They rely on a fixed neural network trained with a fixed number of users. But that makes no sense. The moment the number of users change, the model breaks. So to reach this goal, we flip the perspective, okay? From user-centric to what we call master-centric. And this helps us to use recurrent neural network, and in particular, BLSTM network, to reach this goal, while remaining lightweight enough for efficient training, okay? Well, respect to training, for training, we first start thinking about supervised learning, but we quickly realize that generating dataset would require centuries. So, welcome supervised learning, but the problem is, how do we make it work? Well, we had spectral efficiency as a metric, but we can optimize it directly because binary output causes the gradient always push through the same connection. So to solve that, we design a probabilistic approach. During training and only in that phase, the output of our network are treated as probabilistic distribution. But of course, we weren't satisfied yet, so we trained the entire system in a fully distributed way, okay? And each master P train and run its own network, using only the information from a limited set of neighbors. This means that the whole system is distributed, parallel, and scalable, because when the network grows, only new IP need to be trained. Everything else stay intact, okay? So, and the results, well, much better than traditional heuristic and actual heuristic, as you can see. And not only in terms of throughput or spectral efficiency, but also in terms of energy efficiency. Our model can naturally avoid connecting unnecessary IP. And yes, you can find it on archive, okay, so if you want. To wrap up, the network future must be distributed, energy efficient, and invisible. And to get there, we need to shift our paradigm. We need to go self-free. Likely AI is already helping us to find smarter, scalable solution, okay? So it can accelerate the path toward that future we all hope for, a future without frustration. So thank you very much.
Thank you, Giovanni. And the contribution is open for questions, curiosities. If any? Yep.
First of all, congratulations for your presentation that is there's been a little before mine that it deals again with the self-free. So the topic is the same. The approach using the AI, the LSTM, is of course efficient in terms of results in the testing phase. But you know that the burden of the approach is in the training phase. So how is it how it was complex to train the network, considering a very articulated and complex scenario like the self-free environment? How is the training burden of your system?
Difficult question. Yeah, thanks. Very difficult question to answer. Well, we simplify all the process. Obviously, write the code and make everything work was difficult. Okay, but at the end, we have a limited chain of LSTM because we see a limited set of neighbors, and the output is generated directly to that space. So the training can be parallel. Okay, so each master IP can train its own network in parallel, and that single network is not so big because we limit the area, okay, of inference. So the difficult part is the study and the definition of all the system and build the system. But the training part was almost easily. Even if we don't have 15 PC, so we have run it sequentially on one PC. So this is the border part. Thanks.
Other questions? It seems it's not the case. Thank you again. And then we come to the last to the presentation of Claudio Sacchi, just speaking, entitled "Breaking the Barriers of the Cell. Will the future of the global coverage be self-free?"
Okay. Where is the presentation? Okay. Perfect. And then I have this. Okay. So, good afternoon and welcome to my presentation that is going just after the interesting presentation of Giovanni. Maybe the order should have been reversed, but it's okay, the same. In my presentation, the previous one, my presentation has a title that is like a stone thrown in the pool, because it substantially discusses one of the pillars of modern wireless communication system, the cellular concept. And the question in the subtitle is, will the future of global coverage be self-free? I wanted to share the presentation with my colleagues of the Infinite Cascade Call who cooperated to this presentation. So let's start with some grammar definition of cell taken from the Oxford Learner Dictionary. First definition in order. The first definition is biological. The cell is the smallest unit of living matter that can exist on its own. Second definition on the dictionary. This one, a room for one or more prisoners in a prison or police station. Third definition in the dictionary, each of the small sections that together form a larger structure, for example, a honeycomb. So, which of these definitions are more appropriate to mobile networking? Apparently, the first and the third, because the cell is the elementary part of a structured framework that is the cellular framework. It is indeed modeled like a honeycomb. And what about the prison? In order to understand whether the prison image is appropriate for cellular networking, let's have a look to the evolution of cellular networking. Let's start with the 2G cells, the GSM cells, that were characterized by a large radius of around 1 kilometer. Let's see now the evolution toward the 4G cells, LT. The radius of the cells decreased of 1/3, so on average, so that in the area of a big cell of the 2G, we have many 4G cells. And the trend of 5G and 6G is to decrease further the radius of the cell. So, but why we have such a cell and user densification? For some very good reasons. Because we can increase the capacity with decreased power, we can obtain augmented scalability, and implement green networking because we are spending less power and less supply power to operate in a cell at higher capacity. But we have a problem. Does this approach goes toward the global coverage? Apparently, the cellular networks ensure global coverage. But really, the global coverage is mimicked by the handover because in a cellular network, the association between the user and the cell is univoc. So the user communicates with only the base station of the cell. And so in order to move from one cell to another, there is need of an operation. The operation is the handover performed by an entity, the mobile switching center, that is well beyond, well above the physical infrastructure of the cellular network. So the handover is an operation that is managed at centralized level, where the master node of the network know that the cellular is moving from one cell to another. Then the first connection, the current connection, is switched off, and the second connection is switched on and substantially activated. So, is this approach efficient? We can raise this question because the handover frequency dramatically increases with the cell, dramatically increases while decreasing the cell size. And you can understand that this may be problematic. So now let's suppose to come back to the original point. Let's consider the cell like a smaller and smaller prison cell. Question, who is the prisoner? This is the situation. In the 2G, we have a very big cell with a small capacity, then the capacity increases but is constrained inside a smaller area. And the prisoner is not the capacity, just the quality of service. And so, in order to explain why, let's consider a kind of a legal court against cellular mobile communications, because we're speaking about jail, and so something inherent to life and to the legal. And so we have a kind of a Perry Mason-like trial where the public prosecutor shows his accusations against the cellular network. So the coverage of mobile communication is de facto local. The handover is just a switch on, a switch off of the connection managed at centralized level, even though it can become softer and softer, but it's a switch on and switch off, and the frequency handover limits the user mobility and the quality of service. Then the cellular communications are unfair. The users at the cell edge are penalized. The defendant may raise a very reasonable objection. The history of mobile communication is a 40-year-old success story. Do you know any alternative? The counter-objection is the alternative now exists. It's called self-free networking. May the self-free concept allow to the quality of service to break the bars of a mimicked global coverage? Let's see. In a self-free concept, instead of the centralized handover, we have a multiple access point that cooperates via a central process unit. The cooperation is a full transparent to the user and managed in software-defined network. And substantially, the terminal, the user may be served by many access points cooperating together. So the network follow the users, and this change the paradigm towards a user-centric approach, contrasted with the network-centric approach of the previous of the current cellular networking. And as there are no cell edge user by definition, the unfairness of cellular network is overcome. But so how can we extend the self-free concept toward the idea of global coverage, so breaking the bars of the cell? Yes, in the Infinite project, we conceived a visionary solution using the satellite instead of the access points. And with Starlink, we can implement this. So practically, the global coverage is obtained in order to complementing the terrestrial network in isolated, harsh environment with improved robustness, so the freedom to switch to a new satellite if the old one is obstructed or shadowed, and thanks to the diversity, we can increase the capacity in order and to use multiple satellites to increase the rate. So in the Infinite project, my colleagues, some colleagues of mine, of Parma and Cassino, designed a scenario that is outlined here, and the results demonstrated that increasing the number of satellites, we can increase the diversity and increase the data rate and reduce the outage. So the approach may work. The basic question, would self-free concept enable global and seamless coverage? There are some pros and cons. The pros are no cell edge user, and we're gaining system fairness. The robustness is against shadowing is demonstrated, and the AP cooperation provide higher throughput. The open challenges, the synchronization and coordination of the satellites, it is not trivial. And then we have to manage the dynamic user satellite assertion policies, and the need of channel phase precompensation at satellite to successfully combine the signal at the receiver. This point has been considered, the last point has been considered by my colleagues of the Cascade Call in a JSAC paper submitted in last days, where the multiple antennas at terminal level are used, extending the MIMO concept in order to take signals from different satellites, increasing diversity and efficient of beamforming. So that's all. And for if you need some other information, contact me. And thank you for your attention. And if you have a question, please ask.
Thank you, Claudio, for the interesting presentation, and contribution is over now for questions. If any. Yes.
Thank you for the presentation. The concept of cell-free coverage is very interesting because planning may be easier. But a quick question about the capacity. So looking at the capacity of LEO satellite coverage, the number of satellites you can see simultaneously, say on the territory of Italy, can be in the order of tens of satellites. So it is very useful for rural areas, but where terrestrial coverage is available, the capacity probably is much higher, and compared to the satellite coverage. So it's better, to investigate on cell-free terrestrial coverage. That's quick consideration.
Your consideration is correct, but the 6G targets the global coverage. So when we are speaking about global ubiquitous coverage, we theoretically should reach a point of the Earth and another point of the Earth even not served by terrestrial networking infrastructure. This is one of the key issue of the key requirements of 6G. In this framework, the satellite backbone in the sky can complement the terrestrial part. The terrestrial part where it works is okay, but the satellite complements the terrestrial cell-free part, providing an extended concept of cell-free, where the satellite can really connect not only also areas not covered by terrestrial communication. Without the cell-free concept, this could be unfeasible, because in the past we assisted to the failure of many projects where substantially the terrestrial coverage was patched by point-to-point satellite connections that were useless. The cell-free concept, with the extension of satellite of satellite backbone, can extend the cell-free concept to worldwide. So I think that the integration of the two technologies could really address the 6G requirements.
Other questions? If not, thank you again, Claudio. And we'll...
I had I asked to show the advertisement of an event, if you have time, just 2 minutes. Do you have the slide? I sent a couple of slides of the advertisement of an event. I am organizing a summer school supported by the IEEE ESS with the patronage of the Italian Space Agency and also of the Restart program about, the title is Frontier Technologies for Space 2.0 Communications, and it will be held, okay, this is, that is, and it will be held in the Italian Space Agency from September 1 to 5, 2025. And this is the almost final program with a lot of very interesting things, of lecture and topics about space, satellite space, and non-terrestrial network. There is also a Restart invited lecture that will be held by Simone Morosi, and there are people working in the Restart, people working in the technical panel of ESS that I am chairing. So if you are interested, stay tuned, because the registration is free, and I will send through the channel, through the channels of dissemination, also the registration module. Okay. If some student of yours are interested, please communicate that. That's all.
Okay, thank you, Claudio. And we come to the last presentation that is will be given by Dario Tagliaferri of the Politecnico of Milano. And the title is Sensing the Future, How Vehicle Network Will Drive Safer Mobility.
Okay, so hello everybody. I'm waiting for a presentation. Okay, thank you. I'm the last speaker, so you know that I think you're quite happy about that. So my talk is about sensing the future, so how we can build like better cars instead of not better cars as we thought up to now, but better cars in terms of safety, so for a safer mobility. So what is my vision of sensing the future? So if I think about 3 words like that, so it's, for me, it's about, they have 2 meanings. The most closer one is about like the technical perspective about sensing the future, so be able to see what's around and predict the motion of the objects to avoid car accident, which is our ultimate goal, but also our strike our vision on what would be the future for mobility. At least what we thought in Polyme, it could be a nice way to represent it. So one way is more technical, the other way is more getting into the real future of mobility. So I want to start with the human error factor in any car accidents, because nowadays more than 1 million people die every year due to car accidents, and more than 90% of them are caused by human errors. So fatigue, distraction, whatever it is, it's our fault, as humans, of course. And so how we can pick the human error factor and remove it from the equation? Because most of our human errors in car accidents are due to the fact that our reaction time is really slow in the end. So 1.5 seconds on average means that at 50 kilometers per hour, I take up to 20 meters to stop. So this creates, in very high density traffic, creates a lot of higher probability of car accidents. So how we can go on with that using technology to avoid it, okay? So the first step has been done, I think that here the animation crashed a bit, but in any case, the first step has been done by equipping vehicles with sensors, so with technology that is able to perceive what's around, to represent what's around, so the surrounding environment, and to take decision on how to maneuver according to what the vehicle per se sees. And we start from, and we want to follow all the progression of the autonomous driving levels that were envisioned. So from level 0, in which we have no automation, so it's a human driver that can control the vehicles 100%, up to highest level, either level 5 or level 6, depending on the classification, in which basically it's the human driver only observes the vehicle that drives and nothing else. So we want to get there. And so to do that, most of the research, and actually a good part of cars today are equipped with a lot of sensors that can be radars, that can be lidars, that can be cameras, ultrasound sensors that are able to perceive what's around and provide a set of functionalities from emergency braking, lane change detection, imaging the environment, so creating a detailed map of the objects that are around the obstacles, around the vehicle, sorry, and also parking lot assistance and whatever it is. So equipping a vehicle with these sensors provide at least a first glance of what a vehicle can do by himself, all alone. And concerning to what we do in Polyme, we started from in recent year, let me say 5 to 6 years before 2025, we started working a lot on how to keep vehicles with proper sensors in order to enable the so-called autonomous driving. In this case, on the left-hand side of the slide, so maybe, okay, on the left-hand side of the slide, you see for what we can achieve with a single off-the-shelf radar that is typically used for emergency braking applications. So it only helps when it detects an obstacle to help you in braking before the accident. What we can actually achieve by exploiting the motion of the vehicle to synthesize an image which has a lot of resolution, much more than what we can obtain with off-the-shelf devices. And we are able to distinguish what are the parked cars, all the obstacles that are around our vehicle. On the rightmost part of the slide, you see that actually, I don't know why the video doesn't start, but in any case, in this rightmost part of the slide, we see what a LiDAR can see, so the point cloud that a typical radar, automotive LiDAR can see, actually. And in the bottom part of the slide, you see the comparison with a radar, the typical high-resolution radar that we can achieve and which we worked a lot in Polyme, with a LiDAR that is depicted in purple. And so we can see that at least with a radar that is a sensor that is much less affected by weather perturbation, we are able to achieve something similar. So we can say that we are pretty good in designing sensors for the single vehicle. Okay, so this is what we can do. And of course, there are many other examples from the literature of what we can do with a single device, with a single vehicle. But actually, what we want to avoid is the use of a single vehicle to design which is its path along the street. Because on all the sensors that belongs on a single vehicle are actually quite limited, both in terms of range and also in terms of inherent hardware capabilities. So you can have a situation like this in which each vehicle perceives only what it can see. That means that, for instance, the pedestrian here is actually below. It's not below the field of view of the radar or the LiDAR of the camera, and so it cannot be properly perceived, and so it can cause an accident, or it cannot be properly perceived, and so the maneuver of the car doesn't take into account the pedestrian. If you want to take into account for any pedestrian, any possible obstacle, we need to enforce a cooperation between vehicles. Because, for instance, the rightmost part of the slide, we see two vehicles and a pedestrian approaching the lane, and even though the pedestrian is beyond the field of view of one single car, the other car can perceive it, and by communicating the presence of the pedestrian, the other car can react consequently. And so we can avoid any accident in this case, at least in principle. And of course, we need to enforce a cooperation between vehicles, so a communication between the two vehicles or more than two vehicles, and not only from one vehicle to the other vehicle, but also from vehicles to other communication infrastructure, like cellular systems, for instance. Why not? Because we can think about an heterogeneous cooperative sensing. Because what we want to get in the end is reliability. So reduce at the minimum possible level the number of accidents, so we can use whatever we have available. Fusing or let vehicles cooperate in terms of sensing doesn't only imply that we cooperate just for extending the range, the field of view, let me say, of the single sensor belonging to the single vehicle. It's not only that case. It's also the case of improving the accuracy in the representation of the environment. So actually improving the capabilities of actually perceiving and classifying what's around the vehicles in the space. Because, for instance, in this case, there's an example that is taken from our publication, and this work actually has been framed within the Isaac Age project within the Restart, is a work in which we had plenty of radar images, very low resolution, because they were taken by off-the-shelf devices that cost very few dollars. And what we wanted to do is to demonstrate that by fusing this data in a certain amount, with a certain kind of like advanced processing, by exploiting the carrier phase that typical radar images as a signature, to improve the resolution and to see some specific things. For instance, a pedestrian that tries to approach the lane, but is actually in a radar image, is masked by the presence of a parked car. And since the parked car is metallic, it's much more reflective. So what we want to do actually is to fuse these images. And that's what we have tried to enforce, assuming that the vehicles were able to communicate properly this data, one to the other, and someone, either one vehicle or the infrastructure, is able to fuse this data properly and communicate the result to all the vehicles, so that all these vehicles can take a decision about how to plan its movement in space. And so the result of this fusion is actually that it's pretty fancy. I like to present it every time I talk about that, because in the upper part of the slide here, the pedestrian is actually me trying to approach the lane. And in each single image that were fused, you don't actually see the pedestrian. You see some targets, maybe some obstacles. But actually in the final image, since we have fused a lot of information, we are able even to see my legs, because these are the two spots representing my legs in space that were spaced at that in that experiment by 40 centimeters. Any AI algorithm is much better to apply to this kind of data, high resolution data, that provides a much better result in terms of classification. So this kind of fusion at the very physical layer helps any autonomous driving algorithm, any autonomous driving technique. And this is only possible because we let single vehicles to cooperate one with the other, okay? So actually, to make them cooperate, we need another kind of technology, because we don't need only sensing technology, but we also need the communication technologies. And in principle, since cooperation implies communication, we need something that is usually goes under the name of vehicle-to-everything communication systems. Whatever is the type of communication that we are considering, from vehicle to infrastructure, vehicle to vehicle, vehicle to pedestrian, why not vehicle to network, where network means cellular networks, or in general communication wireless networks, we end up with V2X communication system. And this is the backbone for any information exchange among vehicles that allows cooperative sensing or cooperative maneuvering in the upper case. And that's exactly, V2X is actually the backbone and the bridge between what we call usually awareness, so each vehicle can perceive what's around, so each vehicle sees the environment in to some sense, to some broad sense, to cooperative perception, so each vehicle see what's around and share with the other. So the network of vehicles get to a collective perception of the environment, to our ultimate goal, which is cooperative maneuvering for a safe driving. So I don't want only to share what I see with the others, but also I want to drive with the others, all cooperatively. So it's like all the vehicles were like behaving as a single vehicle, avoiding car accidents, which is our ultimate goal. If I want, if you ask me what's my vision for the future that gets to that ultimate goal, is what we usually call the digital twin. So the upper level of possible sensing that we can have in mind. I don't deep dive into digital twins because we have seen many talks, much more detail about digital twins, but basically digital twins, of what I'm concerned about, is the mapping from a real world to a digital world in which each obstacle, whatever it is mapped, is represented at the maximum possible resolution. And it's also it's also in the CPU of each vehicle, so that each vehicle is really aware of what's around. So basically, we have the environment and its digital replica, and we have something that probably will be based on artificial intelligence that deals with the data exchange between the huge and heterogeneous data exchange between the real world and the digital twin. And of course, since we want to take decisions based on digital twins about maneuvering, we also need some control on the digital twin, because we need that these data are reliable so that we can take reliable decisions. So digital twin, to me, is the future for mobility, for a safer mobility. And to get there, we have a certain number of hurdles to be overcome. Because this is just an example I wanted to show. In this case, luckily, the video popped out. And this is an example of on the left-hand side from the Sakaguchi lab in Tokyo, at the Tokyo Institute of Technology. On the left-hand side is an example of the dynamic building up of a digital twin of the environment as soon as new obstacle, new vehicle comes into place or comes into the area that they were observed. While on the right-hand side, you see that the digital twin is used, at least as a preliminary result, which is, by the way, it's great. It's used by the authors to plan the route of an autonomous vehicle, which in this case is a robot. So, of course, this is a bright look into the future, very promising, but it's only one single vehicle. We want to have it for, networks of vehicles, for managing the traffic, not only the single path, okay? So this is lab testing. What we need, actually, this is actually the slide concluding my talk, is a kind of a run, a hurdle race, let me say. I wanted to call it that way, because we did a lot more steps. We as a researcher, we care about in-lab testing because we want to demonstrate to industry that we are able to envision a certain kind of future with kind of lab testing we have seen in these slides. But actually now we need also scalability because we need millions of nodes with very low latency to be held. Interoperability, so we need standards. Of course, some standards have also been involved in the V2X and general vehicular scenarios. We need cybersecurity because security and privacy, if we want to take decisions based on the sensor data that I've shown you, are very, very important because spoofing can create many problems in driving. And also from the industry perspective, which is a bit farther from us, is the cost and return of investment to make any kind of driving very affordable, very human-friendly. And to end it, I want to end this presentation by saying that the future of vehicle mobility is safe, but to make it safe and to make it more human-friendly, we actually, paradoxically, need to take the human out of the loop. Thank you very much.
Thank you, Dario. Questions for Dario? Anyone? So let me start with a question regarding one of the points that you mentioned in the last slide, cybersecurity. Mm-hmm. Fusing information may expose a system to errors because you may fuse information which is not completely reliable, and that's true in general, right?
Or even corrupted.
Yes, right. But in some cases, you can inject information on purpose, which is something that can be fused with your information, generating an effect which is not what you expect. Exactly. How do you see, this additional vulnerability which is due to cooperation?
Very good question and very difficult answer because what we want to do is to fuse a lot of information because we need it in the end. But this kind of fusion makes a lot of sense only if the information coming from each source is perfectly reliable. If something is not reliable, we probably need to leverage something that, the extension of what we knew from communication system from the security perspective, but mapped at the physical layer even, and not only for communication system. Maybe security for sensing systems may be a little different. I'm not pretty sure about what will be in the future for that, but I'm pretty sure that will be a major research topic because up to now, even in Polymy, all the results that we presented are really beautiful according to me, just because I was involved in that, sorry. But it was assuming that each data were actually absolutely reliable. So no inject, no jamming, no spoofing, no corruption, because it isn't a problem of corruption maybe, because maybe they have some sensor that fail, the failure, that's something that doesn't not even taken into account. And you can see the effect over larger scales if you really enforce the cooperation, and you see the effect that you have when you take decisions. So physical layer security may be an answer, and I know that there are a lot of research about it.
Thank you. Other questions for Dario? Curiosity, comment? Yes.
Hi, Dario. So, yeah, one topic was the cybersecurity part. The other one is about latency. So I was wondering if you investigated the effect of cooperation on the latency of the final decision in the project, or even outside.
My honest answer is not, but a less honest answer is, okay, not yet.
Okay.
Because, of course, latency, if you do it like repeatedly, these kind of fusions, you need to fuse it according to some form of trade-off between performance that for the moment, we have just looked to peak performance, the best we can do, the upper possible sensing, with a trade-off with complexity and latency, as you said, because you need to take this kind of decision. So you need to, for instance, to create these high-resolution maps, really, especially in a trafficked area, very often. This implies maybe doing 10 times per second, maybe. And this information, and from that moment, this information starts to be kind of obsolete. And so I think that the latency problem comes from two reasons. The latency of the sensors, because the typical duty cycle of the sensor is not the one that we expect from typical communication systems that work continuously. And communication system as well, because if you have peaks or outages of capacity, that information doesn't flow as expected. So the latency is the other big problem, because we didn't try to make it a real car to drive by himself, cooperating with the others, using all this amount of sensors. Maybe if using cameras, lidars, you see many works in literature that say multimodal sensing, but the amount of data that you need to exchange, even with compression, with AI, is very, very huge and requires an ultra-stable and ultra-low latency communication link that is not only from one vehicle to the other, so we drive with 2 cars, but we want to drive with 10 cars, and so what happens? I think that the scaling factor is the other side of the coin of the latency. Latency means problems of scalability in this case. Yeah.
Thank you. Any other? No? So let's thank Dario again. So this concludes this session. We are a little bit ahead of schedule, so we are moving a little bit earlier the end of the program. So the next will be the coffee break, and then we have the demo session, the last one in the demo room. However, considering that then at the end of the demo, we will have the awarding of the best demos based on your votes, we prefer to move also the awarding session in the demo room. So before ending this session, we switch to Italian again, and I ask Nicola to say some concluding words for this part.
Thank you, Antonio. I just want to thank the people that make this event possible. So starting with maybe I see Frederick II and those with descendants. I see here Daniele. Yes. I don't even try to mention people because I'm sure I will make mistakes. I will omit names, and then I will be also, let's say, criticized about the way I say people's names. So there is Stefania here that knows what I'm talking about. So thanks above all to the Naples people, and then to CNIT people. That is always a very great resource to make these things happen. And then, of course, to the Restart administration. But above all, and once, I often forget to do it, but the real soul behind all this is Antonio. So I really ask you to thank Antonio for the great work that he always puts behind this organization. He's always unsatisfied. He seems unsatisfied, but being unsatisfied, he makes sure that things improve. So thank you, Antonio. Thank you to all of you for being here, and let's move to this very nice demo room. Thank you. Bye.